Alright, in today's video, I will talk about the problem frame up. So what we want to do in this problem is we can create a graph and connect all the frames that are at the bottom to the ones that are on the top. And to do that, we will just use a loop and just check for all of the frames where it's supposed to be and check if any letter is on top of it. So if there's any letter that is not the frame itself, then that means whatever that letter is on top of this frame. And then after that, we can just use DFS to loop through all of the possible paths. So here's the code. To loop through the frames, we have to keep track of the top row, the bottom row, the left column, and the right column. So if you do that, then you'll be able to loop through each of those four lines, so then you can get whatever is on top of that frame. So here, this is where we're reading the input. I will also use n to keep track of how many different frames there are. So if this is not visited yet, so basically if this letter was not visited yet, then that means it's a new frame, and we can add that into our n, and also set this to visited. Here this is the part where we get the columns and rows. So to get the topmost row, we will just find the smallest row among all of these positions. To get the bottom row, we can just find the maximum of all. And to get the left column, we'll just find the minimum of all the columns. And to get the maximum column, or the rightmost column, we'll just get the maximum of all of these columns. And finally, here we'll store this letter into our 2D array to keep track of it afterwards. And then here, this is the part where we will just check if everything is on top of this frame or not. So this is the first part. We'll try looping through the top. We'll try looping through the left column and the right column. And here, this is the first part. SC, this is our which we defined here. This will be our left column, and TC will be our right column. So this part is the right column, and this part is the left column. And so we check if this is supposed to be the letter that we want, which I set a loop here outside. So if this is not the letter corresponding to this current one, then that means this frame is covering our this current frame, which means that this is on top of this letter C. So here I will just create a graph outside and keep track of all of these positions. So this way, at first I will set everything to 1, meaning that this A is on the bottom of B. And here, if this one's on top of C, then we know that there's definitely no way that this letter can be on the bottom of C, because it's covering C, so it should be on top of C. And so if it's on top of C, then we will make sure that C is on the bottom of this one. But here, instead of giving it 1, we will give it 2. This will mean that this is definitely on the bottom of the C is definitely on the bottom of this G, I, and C. So this is also the same for this right column. We also do this, but change the variable names. And then here we will use another loop to check the top row and the bottom row, and also set them to 2 if C is definitely on the bottom of this one. So at first I set everything to 1 because there might be frames that are not covering each other at all. They could just be in separate positions. For example, here, this frame C and frame A are on different positions, so they won't cover each other at all. And that way, you can, if there are only these 2 frames, you can rearrange it in any position you want. You can put A first and then put in C, or put in C first and then put in A, because afterwards the result will always be the same since they're not covering up each other. And so this is what this 1 means. We can try that out, but this 2 will mean that it's definitely on the bottom of this other frame. So here we'll use DFS, and I'll keep track of this amount of visited nodes, And here the visited nodes are just the frame letters. And also P will be the parent of this current letter. So because we're using a DFS and we want to print out the answer afterwards. So here I will start at 0, and this L means that we've visited 0. This will mean that we've visited 0 frames yet for now. And here this is the L. If L is equal to this N, then that means we've visited every frame. Then we can print out this pass. But here we also have to check that this frame is in a possible position. So we'll use this check function to loop through all of the other frames and check if we haven't visited this frame yet, but this frame is on the bottom of this current frame V that we're already visited. And so if this is equals 2, then it means that this is definitely on the bottom of V. So U must be on the bottom of V, but we still didn't visit UV yet, but we've already visited V. And so this will not be a possible position. So we should return 0, and this function will just break and go into the next recursion. Otherwise, this will return 1. And so if it returns 1, then that means this frame V can be on top of this U. And here we will check. We'll first make this frame visited, and think of this as nodes. So we'll visit this current node and loop through all of the other nodes and check if we didn't visit them yet. So if we didn't visit them and they're one of those frames that we want, because here this is why I said this FC. FC will represent that this frame C is in our current graph, because I set everything from 1 to 26. So this is all of the possible frames from A to Z. I set all of them to 1, but we don't want to visit the ones that aren't actually shown in this graph. So if they aren't shown in this picture, then we will just continue this. And if it's shown and there's a path from this U to V, U is our current frame. So this will mean that U should be on the U can be on the bottom of V, and that way we can look at V next and see whatever is possible after that. But we also have to make sure that V isn't visited yet. And here we'll just change the parent of V to currently to U, and we can change it back afterwards because we might find other possible positions. So here we'll use DFS again, but this time we're looking at the node V, or you can say you're looking at the node, you're looking at the frame V, and you increase L by 1 because now we just visited a new frame. So after this, if we've looped through everything, then this U will just set to 0 again. So that means we can visit U again using some other recursion in another possible path. So here in the beginning, I will set everything. I will set all of the frames to be connected to this 0, and this 0 is basically just nothing. But if we connect it to this, then this DFS will just work out well, because then it will do basically the same thing as what a frame would do, and just loop through all of the ones that it can visit. So this will also do the same. And then if we found one that where L equals to N, that means that we've visited all the frame, and this is a possible path, because we will always check this current node every time we do the recursion. So if this is a possible path, we'll just print this out. And so this is why I saved the parent node. So here we'll just look at the current node. If this is 0, then we'll just stop this recursion where we print the path. If it's not 0 yet, then we'll print out the parent of this V first, and then print out our current V. But here I just increased it by this A because I changed this V to an integer, so we can store this more easily. And since this recursion is on top of this printout function, is on top of this print, then that means that we will loop all the way to the end first and then print out. So we will print out all of this in the reverse order, and that's what we want for this path. So this recursion will just keep on going on, and since you start at 0 here, you just loop through all of the possible paths. And also because you are starting at 1 and looping to 26, this will guarantee you that you always select the smallest. You always select the smallest frame first, and then do DFS on that. So whenever you print, you always print this out in the correct alphabetical order.